All right, good morning everybody. My name is Jonathan Clark from Florida State University, along with Christian and Taylor. Today I'm going to be talking about some work that my graduate student Max Austin has done recently about legged locomotion in fluids. So we just wanted to go here to talk about developing different types of grounds for our robots to move through. My goal is to extend our abilities to go beyond just ground, but to also interact with fluids as we use our legs to move through the world. Now, animals are capable of moving through all kinds of crazy environments, and we'd like to imbue some of that agility into our robots. So I'm going to momentarily decompose this incredibly complex world that we live in into three different domains. Terrestrial, which we all understand really well in this community. Scansorial, so climbing robots, which I've happened to be working in for the last 19 years or so. And then over the last couple of years I've been looking at aquatic and how do we move through water, either like this moves above or below or on the bottom of wet environments. Now, fluid dynamics is complicated. I'm not truly a fluid dynamicist by any stretch of the imagination. There's lots of different ways that you can model the complexity of moving through these kinds of fluidic devices. So all the way from full multiphysics down through simpler and simpler forms. The approach that I'm going to take stems from my background with reduced order dynamic models, and so I'm going to start with these kinds of reduced order dynamic models and just add just a little bit of complexity. And say, by just adding a little bit of understanding of the fluid dynamics, simplifying it, can I get enough insight to guide the design and potentially control of our robots that are going to move through these wet environments? Now, animals move through fluidic environments using different techniques. Depending on the type of animal. We can break these down into a couple different modes. One is a drag-based propulsion, which is used by a lot of terrestrial animals. And then as you move towards more primarily aquatic animals, you're going to be using a lift type of motion. Now the lift type motions are faster and more efficient, as begets an animal that spends all the time in the water. But a lot of the animals that we see that are primarily terrestrial and then use aquatic modes intermittently, like we do, or squirrels, or dogs, or lots of different kinds of mammals, they tend to use a drag-based motion, using their limbs similarly like they do on land, but creating drag forces by interacting with the fluid. So that's where we're going to start. Now, as a side note, I'm going to talk about climbing first, as one does when one launches into swimming. So I've been working on climbing things. We looked at studies with Bob Full and Dan Goldman about Keller Autumn of the climbing of geckos and cockroaches, extracted reduced order dynamic models, analyzed those models, and then built robots based on these models that can climb dynamically up vertical substrates using these kind of oscillatory behaviors that we see in the animals, where they swing back and forth and use these pendular dynamics to do self-stabilizing climbing. And in the bottom right, you can see we took this and tried to emulate a flying squirrel by encapsulating an airplane around a robot so it can dive off of a wall and then pull into a glide and glide away to the next location. Okay, so why talk about climbing robots? Because this was our point of departure for introducing the water. We noticed there's a striking similarity in the gross body motions between a human swimming in the crawl gait and the kind of climbing motions we're doing with our robots. Now, these are different domains in different directions, but these are both, you can think of these in the horizontal plane of similar types of motions. Now, we have models for horizontal plane reduced order dynamics, right? We've got the Schmidt and Holmes, the lateral leg spring model. We have the version that we've been using for modeling vertical things. That same model, we're saying, can we extend that to swimming, thinking about the horizontal plane in the aquatic environment? So we took this model, so this is the point mass Fogelman model, and as you can see on the left how it's sort of bouncing back and forth as it climbs up the wall. We think of it as point mass, springy legs, actuator on each leg, and it pulls itself up, and it alternates between right and left feet. And so we've translated that to the aquatic environment by having a centralized body that has mass that's treated as a sphere. We have two limbs. Each arm can retract. Each hand has a sort of a plate or something which can pull against the water. And then we look at the forces, the velocities of the hand and the body relative to the fluid, which allows us then to compute drag-based forces from the hands and the body on the water, as well as the springs or the internal motor forces of the robot itself. Combining these forces, we can write the equations of motion. We've got forces on the left and right arm, forces on the body, and we put it together and we calculate equations of motion. They're very, very similar to the equations that we use for climbing. Matter of fact, shown here are the equations that we use for our bipedal dynamic climbing model. In gray are the addition of the fluidic forces. So to switch from a climbing mode to a swimming mode, at least in model world, all we have to do is substitute these out, drop out gravity because we're traveling horizontal to it, and now we have a model that gives us ability to capture some of what's going on in the fluids. So I'll spare you all the details of the analysis of this, but the quick version is the robot that we built, Aqua Climber, is designed to climb vertical surfaces like you see on the left, swim across horizontal in the water using the same kind of motion, and on the right you're going to see a transition between the swimming and climbing modes. Note that this robot only has 2 active degrees of freedom. One motor controls the front arms, the moving of phase lock, simple sinusoidal trajectory, and the back one controls the rear legs, which controls the relative roll of the body. For swimming, allows the one foot to leave the water for more efficient retraction, and during climbing we lock those, and so you can do the standard bipedal dynamic climbing. Okay, so that's the horizontal plane. More recently then we've been looking at what happens in the sagittal plane. We're all familiar with the slip model of running, which many of us are, and so we've taken the basic slip model of running and we've adapted it in a similar manner for moving through fluids. And so to do that, we've classified the forces acting on this model in threefold. One are the internal forces, right? So you got your spring damper forces and your torques from your motors. Then we add field forces to it, we have gravity and we have buoyancy. And then we add the hydrodynamic forces from the body, from the leg, and then we put them all together and we get equations of motion that look very similar to slip with the addition of these hydrodynamic terms. The nice thing about having this kind of model is that it allows us to, with the same model, with only minor control variations, run in the air, run underwater, or to move across the surface of the water. This in turn gives us the ability now, we have reduced order dynamic models for climbing, for swimming, and for running, and they're all essentially the same type of model. With this, then we can use a design philosophy where we take our target dynamics, how we want the center of mass to move in these kinds of motions in each of these domains, combine them together, and allow us to examine different leg morphologies. There's 3 that we examined for the robot I'm going to show you in a minute. Calculate the mappings, add constraints for the particular robots, including motors and actuation and ground contacts and stress and strain. And then we can generate candidate legs, optimize those for the ones that give us the most efficient or fastest or best balance of motors or design for each of these things modes. So this is the leg for our quadruped that came out of this design process using each of these models. And so this is a picture of the robot. This is the first steps. This is a very new robot, so it's just sort of walking along on the ground. What's interesting though is the design of these legs, although it looks similar to the earlier like Minotaur robot that we were using, have specifically optimized for this, for climbing behaviors here. Turns out that this type of leg morphology works better than the RR or other types of 5-bar leg linkages for climbing. Here we are on purely vertical terrains. In addition to climbing on vertical terrains, we can also move through the fluids, and so you see here a video of it transitioning from walking on the ground into the aquatic mode, and you can see some sample swimming in our little baby tank outside of our lab above. And so, with that, I'm going to conclude the presentation and open it up for questions. Thank you very much.
The LLS model, I guess, for swimming, was the drag the same in both directions?
So we've looked at different hand designs to give us differential drags in each direction. In the horizontal plane model, for our particular robot, we were using body roll, so during the recirculation we were moving through air. So when we were modeling that particular robot, we had a differential drag when we were moving through the air and through the water. For the swimming models, it has
even in the simple model.
Yeah. But you can generate motion using the same thing just by differentiating the velocity between your reset and your power strokes. So we allowed to do either way.
Yeah, I was struck especially about watching the last one with the quadruped. It looked like to me everything you're doing is like what I would do with my arms.
Yeah.
But not what I do with my legs.
Correct.
You're not actually doing kicking motion.
No, we're not looking at kicking motion, especially the climbing ones, the horizontal plane one here. We're modeling just the arm-based motions of this.
I might be totally off base here, but I feel like when I swim, I'm getting most of the mileage out of my legs doing that kicking motion. So I was just wondering if you thought about this or looked at this, because especially looks like on the quadruped, you could do a pretty good job of that.
Yeah, so we have looked at it a little bit. Similarly, when I learned to do rock climbing, they said lift with your legs. Right? It turns out that animals and the stability of your system works better if you're climbing with your arms. But we as humans have much more powerful legs than arms, and so it makes more sense to use our legs. I think that carries over for the water as well. Now, we did do some work where we were comparing the motion of our legged systems to the swimming of dogs. I didn't show it here, where they use the front limbs and the rear limbs slightly differently when they're swimming. And so we can do a little bit of, we can use this model to look a little bit, but as soon as you switch into closer to what we're doing, all of a sudden if you're doing some kind of a kicking motion, you're switching from a drag-based to a lift-based motion.
Which is better.
Oh, it's much better. It's faster, it's more efficient. But where these models are explicitly capturing the drag-based. We've done some other work on sort of capturing lift-based motion, but I wasn't talking about that here. We can talk afterwards about some of the details of that. The models get a little more complex if you want to capture that in a meaningful way. But it's possible. Yeah, great questions. All right.